take their seats. All right, cool. Hi, my name is Anthony Grasso. I'm here to present to you lessons learned with data modeling in Cassandra. Before I get into the presentation, if everyone can hang around after, we'll be bringing up, I think Tim will probably have a few things to say, and we'll also be bringing up someone else to say a few words, just quickly. Also, if you can please hold questions off to the end, that would be great. So today I'm going to be talking about my company's migration to Cassandra. I'd like to talk a bit about what we've learned from doing that migration, particularly with modeling. I'm hoping you will all get some information out of this about maybe how to do data modeling in Cassandra, and also, I don't know, maybe some understanding of how it works as a database right down near the bare metal. So firstly, a bit about me. I am a Formula One tragic. I will stay up late to watch the sport. I will get up to all hours of the morning to watch the sport. I'm also a football tragic, and I will do exactly the same thing. I will stay up late to watch the sport, and I'll get up early to watch the sport. So a bit about the company. So Circa actually started out about 16 years ago, and its goal was to help universities do research in financial markets. And they were quite successful at that, and as a result, commercial entities started getting wind of this, and they wanted assistance as well. And so Circa spun off a commercial entity and to assist commercial clients. And that commercial company is known as RoZetta. So essentially Circa owns RoZetta. They still do, both entities still do the same thing. They still provide insights into data. It just so happens that Circa still services the academics, where they provide insights into financial data for academics, and RoZetta provides insights for commercial clients into market data, and that can be anything from real estate domains to financial domains. So I want to talk a bit about our product, our flagship product, Tick History. When we did this migration, because we've done it already, it's been a while since we've done it. When we did this migration, the system was around 350 to 400 servers across 2 data centers. It had a bit of data that it was storing. It was around 150 terabytes of instrument data. And so when I say instruments, I mean sort of stocks. So example, BHP, Combank, stocks like that, basically. It was generating, 1.5 terabytes of data every fortnight. We had around 50 trillion records overall throughout this data. And there was, originally, it was very much an enterprise system. It was heavy use of NetApp, heavy use of MySQL type databases. We had all our data, the majority of the data was in flat files sitting on NetApp. We had a couple of MySQL databases actually storing data as well, and a few to do user support. So essentially, Tick History just allows you to search for an instrument, like a stock, for a certain period of time. So if I want to look for BHP, for example, 2 weeks ago, I'll just put in the stock, put the date in, run a search, it'll give me back some data. I can also put in like a range query for data as well between certain dates, and I can specify, more than one instrument if I want. So let's get on with the challenge that we had to do. Basically, we had an instrument pricing table that sat in MySQL, and this was around 5 gigabytes at the time of time series data. It was around 60 million records that spanned 30 years, so it was a bit of data. And this thing actually grew at around 100 gig a month, and that growth rate was also growing as well, as data tends to do. And this system here gave us around 3,000 requests a second for performance on a good day. One of the reasons why we wanted to migrate away from this was the read performance was absolutely shocking under heavy load, to the point where some systems would grind to a halt. We had a service which would summarize the daily trading for each exchange throughout the world, and this service would not only read from our filers to get the flat files, it would also read from this database. And when this database underperformed, everything would just grind to a halt. So that was our first problem. Our second problem was it took a significantly long time to load this database. We're talking weeks here just to push this data into MySQL. And that was bad because if we ever had a failure and we ever had to reload, we would have to go to our DR site, and then our DR site would be the main thing for quite a long time. Fortunately, we never had to do this, but we were worried for quite some time. And lastly, one of the other things we found was at some point in time, it corrupted one of our tables, which wasn't nice to fix. And so we found it not to be the most reliable thing. So we started looking around for solutions. We needed something scalable. We needed something that was resilient. We needed something that we could grow over time, so to expand. So as more data came in, we could eventually upgrade. We looked at a whole bunch of things. And for us, Cassandra was the thing that fit the bill. Basically because it fulfilled all the things we wanted. And we also found out that it had really good write performance, which was a big win for us because we could load data in really quickly. The last thing that really sold us was it was open source. And so we're like, yeah, let's do it. So management came to us and said, look, this database sucks, upgrade it to Cassandra. And so we're like, no worries, challenge accepted. So, like all good engineering teams, we went in, kicked the door down, guns blazing. So we thought, well, this isn't a really hard problem, right? It's just instruments over time. It's a two-dimensional problem. We'll do the same sort of things we've done with MySQL. In MySQL, the primary key was the instrument code, so the row key can just be the instrument code. And then we can just grab all the data for that particular instrument and just stuff it into the columns. So we thought this would be a really good way to go. And so we ran with it. And so, easy, right? We could finish up in the afternoon, grab some drinks, and be home. So we ran some tests, and I can tell you, it was a total epic fail. It completely tanked, and we were standing around scratching our heads going, what's going on? 2,000 requests a second, why isn't this working? The problem was at the time we didn't understand Cassandra well enough. We didn't understand what was going on, and we needed to really look under the hood to find out what was happening, to get an idea of, where we went wrong. So I'm going to take sort of a bit of a step back from this story now, and I want to talk a little bit about how Cassandra stores its data, and because we need to understand this to work out why this didn't work. And if you're going to take away any message tonight or anything, the message I want you to take away is the read performance is heavily dependent on how you write your data. That's like, I'm hoping if you take anything away, it's just that. And I'll explain why. So I think as Alex touched on briefly before, Cassandra stores its data in SS tables, which is essentially just a file on disk, right? And to get an idea of how it does this, we should probably look at the read path first. And I know also Alex touched on this briefly as well, but the read path in summary essentially is quite simple. It just appends to a commit log, updates a mem table, and then returns and acknowledges back to the client and says, yeah, I've written that data. At some point later in time, it asynchronously flushes that mem table to disk to write out that SS table. So I'll put up a diagram, a sequence diagram, to kind of explain how this works in our particular case. So you've got data, commit log, mem table, and SS tables. And so in our particular case, we had instrument data coming in. It was going into the commit log, going to the mem table. Then at some point later in time, this data was actually getting flushed to an SS table. And so that went on. And so you can see instrument data coming in and getting written. So the thing I want to point out, though, is when those SS tables were being written with that data, the first SS table had, instrument BHP, ABC, CBA, right? That's fairly straightforward enough. The second SS table had, ABC and BHP in it. And so as you can see, instrument data for a particular instrument was being placed into multiple SS tables over time. And so, as you can imagine, more instrument data is coming in, and it's going into many more different SS tables. And so, our failed approach looked like this, essentially, after our SS tables were written out. So you can see the row key, which is the instrument code, had many SS tables that made up that row key. So if we wanted to get instrument data, it's spread across those entire SS tables. And so that's just sort of the first part of the problem, right? The to get an understanding of why this really sucked is we need to look at the read path now. And the way Cassandra does its read path is also fairly straightforward. What it does is it goes to the SS table and works out, if that SS table has the column the row key that you're after, gets that result, and then goes to all the other ones that have it, and then merges it and sends it back to you. So basically it's reading all the SS tables that contain that row key in it. And obviously the more SS tables you have with that row key, the more it has to look through. And so to give you an example, if we looked for BHP in our failed data model, you'd have to go through, the first SS table and go, yep, BHP's there, I'll use that. I'll go to the second SS table, BHP's there as well, I'll use that as well. Third one, I can skip, it's not there. Fourth and fifth one, yes. And so it was collating all this data, merging it all together, and then sending it back to us. So we're getting this really wide rows of data. And in some cases, as I mentioned before, all we wanted was like the first day or the most recent day or just a small section. But in order to get that small section, we had to get all the data first. And so that's basically why it didn't work. So we needed to take a new approach on this. So we sought some external advice, and one of the first things they said was, you need to analyze your data. You need to work out what your data is doing firstly. And so we went back, we looked at all the instruments that were coming in, and we worked out roughly that their frequency update was fairly consistent. So they were updated fairly consistently over time. We also had to analyze our queries and work out exactly what we wanted to hand back to the clients. And so really, as I mentioned before, the requests were quite simple. It was just sort of a small chunk of data for a couple of instruments, right? It was just, a week or a day for a bunch of instruments. It wasn't the entire thing. And so the last thing that was suggested is obviously, you had to redesign your schema. You had to reportion your data out some way. And so we had to look for a schema that would allow us to touch only a small number of SS tables when we were getting data back. And so what we did is we looked at our failed approach, right, which is just essentially instruments over time. And we thought, well, we can put in another dimension into that row key so we can narrow down the number of SS tables we have to look at when we go read data. And so we used the time component to give us that index. And so now you've got your big rectangle of data. We've essentially turned it into a grid problem where with two coordinates where we can just index and pinpoint the piece of data we want now. And that worked out a lot more efficiently. So our new approach essentially looked like this. So it was an instrument code with a unit of time. And the column data was just that bit of data for the instrument for that period of time. So we ran some new stats and we got close to double what we were originally after, which was a really good result. And these were on machines that were 8 cores running around 66 gig of RAM. To further verify what we'd done was correct, we ran a tool that is installed on each node called Node Tool CF histograms. And this tool is quite useful. The reading of it is kind of funny though, because you need to understand it. The offset doesn't really mean anything to begin with unless you pair it up with the right-hand column. And so it kind of really looks like this. So for this particular stat, basically the column, the offset becomes the number of SS tables accessed, and then the right-hand column becomes the number of times an SS table was touched, essentially. And so as you can see, the majority of our reads only touched one SS table. It was around 70%, which was a really good result. We had a couple of outliers that hit, 4 to 5 SS tables, but that's sort of what you're after. That's the data model you want. You don't want to be hitting any more SS tables on your reads, otherwise you'll get really bad performance. So, in summary, lessons learned. Basically, the main message, as I said before, that I want you all to take away is your read performance heavily depends on how your data is written. All right, so I hope this kind of explains that. The other thing as well is you need to understand how Cassandra works, how it stores its data. So call back over that information about the read and write path. And you also need to understand how your data will grow. And because you may work out a certain row key partition, But if you're going to get a lot of hits in that particular row key, you're going to start to see that fragmentation like we saw. The other point I will make is your performance degrades over time for bad schemas. I should have put an asterisk next to this because what I'm really trying to say is a lot of people will start up a Cassandra cluster that's fresh, no data in it, and then they'll start putting some information in there, putting some data in, and it'll be really snappy. You'll get back data really quickly. But that's only because it's got a small number of SS tables and it's not very fragmented. But over time, as you start pouring more data into it, if you have a really bad schema, your performance will slowly degrade and you'll start to see the bad results that we saw initially. So you need to be really careful about, you need to think ahead about how you're going to partition it and what queries you want to run. So also on that note, if you are going to do that migration to Cassandra like we did, make sure you're using production data. Don't just put in like a small subset and go, yep, that's good, and walk away. Because you need to do a full test, otherwise you may not uncover these issues until you actually go to production. By then it's too late. Fortunately, we did a lot of testing before we did that migration, so when we came across this problem, we were in the early stages. And so I would advise anyone that's sort of looking at making that migration to actually get as much data as they can and load it in with their schema. So yeah, that's pretty much everything from me. I'm happy to take questions now if anyone has any. So,
Scott?